Welcome back. We begin this section by examining some of the common types of input or information gathering devices. Most input devices are mechanically or electrically operated switches which report a simple on or off state to the logic section of the controller. On-off devices, like switches, are called discrete or digital devices, as they can communicate only one of two possible states at any one time, like yes, no, or on-off. This means that the device is either sending a signal or it is not, and when the switch changes state, it happens instantaneously from one voltage level to another. A limit switch, for example, signals the arrival or departure of an object when that object makes contact with a sensing arm or lever. This float switch will respond to the level of liquid in a container. Normally, its internal switching contacts are open, but as soon as the liquid raises the float to its maximum position, the switch instantaneously changes state, reporting a closed circuit condition to the logic. Here we see a temperature-dependent switch or thermostat. This type of switch has a set of internal contacts which change state when a preset temperature is reached. Here are some examples of electrically operated input devices. This photoelectric sensor will send an on-off signal to the logic when the beam of infrared light is interrupted by a passing object, as shown by the LED indicator. To detect the presence of metal, an inductive proximity switch is used, sending an on-off signal to the logic. There are many other types of proximity sensors, like this capacitive type, which will send its on-off signal to the logic when any object passes within its sensing area. Not every input device behaves like a simple two-state switch, sending discrete on-off signals to the logic. For example, this thumb wheel switch sends coded numerical data to the logic circuits based on a preset numerical value, which could, for example, represent the number of liters of ingredient required for a blending process. There is another important family of input sensors which operate as analog devices, and they are called transducers. A transducer transmits a voltage signal which varies according to the physical condition that is being measured, and this we call an analog input signal. A pressure transducer, for example, will output a voltage signal proportional to the value of the pressure it is monitoring. When we use analog input devices, special input modules are required by the PLC to convert the analog voltage signals into numbers and then into simple on-off information signals that the logic section of the PLC can understand. Let's move on to discuss the output devices. They are generally two-state devices which receive simple on-off messages from the output section of the controller, turning them either on or off. An electric motor, indicator lamp and buzzer are all typical examples of two-state output devices. Sometimes we may encounter an output device which is not a basic on-off type. For example, this digital display device, which requires a numerical output from the PLC, and would have to receive this type of signal through a special analog output module. Now we move on to the third and final group of devices that make up the array of circuits represented in a ladder logic diagram, the logic group. A logic device will usually make a decision when it receives a signal. Then it will activate other devices according to the way they have been wired into the logic. A key device in the logic group is a relay. As previously explained, when its coil is energized, one or more sets of contacts change to their active state, either opening or closing the electrical circuits to which they are connected. Then, when the signal to the coil is interrupted, the coil becomes de-energized and all contacts return to their normal or inactive state. This is how a relay is represented on the ladder diagram, showing the coil and contacts. When the coil is energized, the contacts change state, passing power to other circuits. In addition to the standard control relay, there is a latching relay, which is able to hold or remember its most recent switching state, even when power to the coil is interrupted. Here's how it works. When the coil is momentarily energized, its contacts change state due to the action of an electromechanically driven pole. And when the coil is de-energized, the contacts remain in that state. So it is as though the device remembers its current switching condition. The next important logic device we'll examine is the timer. Timers can be electromechanically or electronically driven, but regardless of mechanism, they both achieve the same objective, and that is to signal a change in state once a preset time delay has elapsed. After the timer has timed out or reached its preset delay, its contacts remain active until power is removed from the timer, whereupon it is reset, ready to begin another timing cycle. The final device in the logic group is the electromechanical or electronic counter, which is used to count system events. For example, we preset the counter to 10 on our block sorting machine using the thumb wheel input switches. And whenever a short block passes the limit switch, a voltage signal is sent to the counter's input circuit and the count advances by 1. When the preset value is reached, the counter's internal contacts change over to their active state and remain there, signaling the next event in the program. When power to the counter is interrupted, the count is reset to 0. So we can see that by opening and closing their contacts at the right time and in the correct combinations, these logic devices control the flow of power in a system. After the break, we'll return to explain how input, output, and logic devices are arranged to create a relay ladder logic diagram.